I will go very quickly. Thanks for the introduction again. And today I'll be discussing some of the research opportunities with the framework that we have just recently released. It's called OpenRAN Gym. And before going into the details of what's OpenRAN Gym, I would like just to give a brief introduction of what is happening in the cellular domain. So we are basically transitioning from traditional black box approaches where all the functionalities are kind of like lying and living inside a monolithic base station. And what's happening is that we are moving those functionalities and we are splitting them as software containers using a cloud-based approach to different components. Those components are usually called centralized units, distributed units, and ready units. So this is basically why we're moving from everything in one box to multiple boxes where the logic lives inside is as distributed network functions. One of the bodies that is trying to specify and standardize this new paradigm is the OpenRAN Alliance. And the OpenRAN Alliance is trying to specify what are the interfaces to be used. Those are open interfaces that everyone can implement using this concept of disaggregated radio access network or RAN. And of course, it's very open to open source contributions. But more importantly, has started deploying what are called the RAN intelligent controllers, which are two components that are designed to execute different control loops. And that's where the intelligence lives in both near real time and no real time. And we will see what this means here with this slide. So on the right, we have the same architecture. To the left, we have different control procedures that usually operators deal with on a daily basis. That means that, for example, we have policies, models, and network slicing control with thousands of devices at a time scale of 1 second and even higher. That can be something that can operate on 1 second, 3 seconds, 1 minute, or even hours. And that's what it's called the no real-time loop control that is going to be executed as our apps inside the no real-time break. Then there are other control loops that operate on a more lower time scale. And those are, for example, when we talk about those time scales are things that go from 10 milliseconds to 1 second. And that's basically what the new real-time control loop contains that will be executed as X apps inside the new real-time break. And that's basically where you handle hundreds of devices. And you are getting data at such as KPIs like number of sessions or PRB utilization, resource utilization, and buffering. And that's basically where you want to perform the control loops in the domain of load balancing and load control, run slicing, and scheduling policy. And then that is being extended to the real-time part, where you can actually associate each resource block to a specific user. You can get IP samples, and that's our control loops that usually operate at a scale lower than 1 millisecond. And you can execute them directly at EDU or there. So now that we have kind of like highlighted what's the current ecosystem, the 5G domain that everyone is moving to this new concept, it's called OpenRAN. One of the issues is that the academia usually is kind of like left behind because it's very hard for us to kind of get access to test beds and experimental facilities to, for example, use AI or prototype new AI solutions and kind of like operate with cellular systems. So we kind of like decided to develop OpenRAN Gym because we noticed that there was a lack of experimental platforms, lack of end-to-end experimental platforms, where there's the RAN, the core network, the SMO, and then the RAN intelligent controllers. There was a lack of data sets. There is also the need for large-scale experimentation. And the overall goal is that we want the academia to be familiar with what's happening in the OpenRAN and with the OpenRAN Alliance. And that's why we have developed OpenRAN Gym. OpenRAN Gym is the first publicly available research platform for data-driven OpenRAN experimentation at scale, and has been designed exactly to facilitate the testing, designing, training, and evaluating AI solutions for cellular networks. This is an open source contribution. You can find the links to the websites here, as well as the GitHub webpage. It's an end-to-end OpenRAN network that you get, meaning that you get the neural time break, you get to interface, you can collect the data, you get an XApp development kit so that you have an empty template where you can place the AI inside of the template. You have tools to perform data collection, data analytics, there is support for network slicing, and it's integrated with Colosseum, which is the world's largest RF emulator with hardware in the loop that is available in the world as of now. If you look at the architecture, there are three main components. So first, we have a neural time break implementation that we have called OpenRAN. This basically comes with the E2 termination, which is basically the tool that lets you connect with the base stations to collect the data and to enforce control solutions, for example, if you want to change the scheduling or the slicing profiles. It also comes with a framework that is called Scope that we have developed, and it is also open source. That basically extends SRS-RAN and OpenRAN interface to support network slicing, scheduling control, and in general use AI to control the base station in real time, which is something that otherwise you would have to recompile the base station every time you want to change a control action. In this case, instead, it's seamless, so you can do that in real time. And then, of course, all the entire stack is open source, so you can program any particular functionalities. And as I mentioned before, this is something that we have developed. It's integrated with Colosseum, but actually, I will see in the talk, it's actually easy to port this to multiple test beds. If we look at what is basically, oh yeah, this is messed up. Let me show all of them there. So basically, oh, this is going very fast. Sorry, let me go. Okay, so basically, Colosseum, as I mentioned before, is the world's largest RF emulator. It's a container-based environment with white box infrastructure. There are 256 software radios that are fully reprogrammable, and it comes with two components. One to emulate the channel, and it's the massive channel emulator. So basically the radios that are called standard radio nodes are generating actual waveforms. And they're connected to the channel emulator, which uses FPGAs to emulate any channel that you can think of. So you can create your own different scenarios. For example, you were just showing three, like a Rome base station deployment scenario, a Boston one. So then we have also emulated the Powder platform deployment scenario in Salt Lake City. You can create all of those different scenarios, play around with fading, mobility, different user distribution. You can emulate that using the actual radios, transmitting in real time. And then you have a traffic emulator where you can create different traffic profiles, for example, video streaming, browsing, or sensing of different components. And this is performing in real time. So it's a real emulation with actual radio. And that's what you can do with OpenRAN Gym. For example, you can cover all the life cycle of AI. You can cover from here to the left the data collection, then you do the model design, training, and testing. You can deploy that as an XApp, which is how an AI is executed in ORAN. You can perform the online fine-tuning of the model if you have to, and then you can do the actual control and inference in real time. And you can do all those things with 4 lines of code described here. So you need 1 line of code to start the neural time break, 2 lines of code to start the GNOD and subscribe to the reg, and 1 line of code to start an XApp. So that's extremely simple, designed to be as simple as possible to facilitate everyone that is not familiar with OpenRAN to take AI solutions, bring them to an actual network that is executing already a cellular stack, and test the AI solutions under multiple deployment scenarios. And that's how the XApp looks like. So there is the first, on the left, connectivity modules, which is where you get the data from the base stations and where you can control the base station. And then to the right, that's where you have the data-driven logic unit. You can do the inference, the prediction, the control, and you can send the data back to the base stations if they're controlling that. And those are all ORAN compliant, already the E2 interface. You can get KPIs, you can subscribe to a few of them, get only the one you're interested in, and then you can plug the AI, and these, you can kind of like make the AI actionable. So if you look at what type of research you can do with OpenRAN Gym, of course, any sort of AI-based control, that includes network slicing, scheduling, traffic steering, and energy mobility management. You can also generate data sets. You can perform forecasting and classification. You can play around with orchestrating AI. You can also play around with spectrum coexistence share. You can do research in reliable AI so that you can understand if how reliable is the AI? Is the AI taking good decisions or bad decisions? How safe it is? And investigate security aspects, perform online training. So those are just like a few selected topics that you can cover by using OpenRAN Gym. And just to give you an idea, I'll just go very quickly through a few use cases to show things you can do, for example. So in this case, we have deployed 7 base sessions with a total of 42 UEs. This has been deployed on Colosseum. So they are transmitting in real time. We are only emulating the wireless channel, but the waveforms are actually being transmitted. We have 3 different network slices, in this case, EMBB, URLC, and MTC, which will be national wide broadband, ultra reliable and low latency communications and machine type communications. And in this case, we have developed 2 XApps that host a deep reinforcement learning agent. And the 2 XApps are executing in the network rig, and they're designed to control 2 completely different policies. So the first one is the Bluetooth here, is the one that only controls the scheduling policy. So you can select, for example, if you want to do round robin, if you want to be using a proportional fairness solution. So it's just that scheduling policy. The other XApp is instead controlling as well the run slicing policies. So meaning that how many resources are actually associated to each slice. So of course, the action space for this XApp is larger. And you can see in the performance here that the blue cube, the orange cube is the one that brings the best performance. And for example, the take-home message here is that you can kind of like play around and see what are the actions that you really want to control to get the best performance. Another sort of research you can do is, for example, how portable and generalized is your AI. So say that you train the AI on a specific testbed or a specific deployment. Can you move the AI to another deployment or another testbed and still get the performance improvement? So you can actually have AI that is general. That's one of the experiments that we have done. So we have trained one AI, the neural agent that we have discussed before on Colosseum only. Then we took the same software container, we moved it to 3 different other testbeds, in this case, Arena, Powder, and Cosmos, which are over-the-air testbeds with completely different deployments, completely different features. And every time you see that the AI starts, which is indicated by this arrow here, you see that the performance improvement for the blue curve, which will be the EMBB slice, which is the slice that we are trying to prioritize, while the other 2 slices are bested for slice, it gets always prioritized. You always get this performance boost with different throughput values, because each testbed, of course, has different capacities, but you still always see the improvement. And that's something that you can do on Colosseum and using OpenRAN Gym. Another thing that you want to, for example, look at is what happens when you have trained your model. Sorry for the, yes, that was messed up. What happens when you have trained your model offline and you're deploying the model on a completely different deployment. And then what happens if something changes or there are conditions that are never seen by the agent? Can you fine-tune the AI to operate better in that specific condition? And we have done this sort of research with OpenRAN Gym. Here to the left, that's the distribution of actions, in this case, scheduling and slicing control, depending for a specific traffic profile. If you see that the actions are distributed differently across the different actions. And as I said, what happens if we want to perform online fine-tuning and online training? You see here below, for example, what happens is that if you look at those 2 plots here, on the bottom left corner, we see the loss and the reward during training. The loss gets reduced. So that's a negative loss. So it keeps increasing, meaning that it gets lower. And the reward is getting higher. However, at some point here, where there is this arrow pointing in this point, we completely changed the traffic profile. The agent was not trained on that traffic profile. I've never seen that traffic profile before. So if you look at the reward, you get a huge reward loss. And then that's when we start the online training. And you see the reward starts increasing again. And that's the advantage of using online learning. And if you look, for example, to the right, you see that once we started with the yellow profile, that's the distribution temporally, then we see that the distribution completely shifts to another distribution. And that means that the agent is kind of like trying to favor different actions that the ones that was trained to use before. And this actually opens to new questions. For example, here to the left, the very bottom left corner. We look at the throughput here. When the model has been trained, you get this blue curve that is not really is kind of stable. But during training, you see that the throughput is oscillating a lot. That means that during the online training, the agent is exploring new actions, and exploring new actions might create a phenomenon where you're exploring actions that are not very efficient. So this opens kind of like two new questions. How much training do you have to do? And you can use OpenRAN Gym to kind of investigate those trade-offs. This basically concludes my talk. I hope that there is space for questions if you have any, and I'll be more than glad to take them.